Okay, the next reaction we're going to cover is dihydroxylation. Okay, again, this is an alkene addition reaction. We start with an alkene, and we're going to get as our final product a diol. That means we have two alcohols, and they're going to be right next to each other. We can think of those diols as being on carbons 1 and 2, which just means they're next to each other. All right. The reagents to do, or in this reaction, because it's an addition reaction, we're going to break the pi bond. We're going to be adding two OHs. Because we're adding the same group, we don't have to worry about the regiochemistry, whether this is Markovnikov addition or anti-Markovnikov addition, but we do have to worry about the stereochemistry, the relationship between these two groups, and that is Syn addition, right? So they're added in a concerted mechanism, all right, and that means the two OHs have to be on the same side of the molecule. Again, in these reactions, we only have to show that when we form two stereocenters or more. All right. The reagent we use to do this is osmium tetroxide OSO4. Okay. And there's a couple ways you can write this. You can just write OSO4, but a lot of older textbooks historically have written this as two steps. NaHSO3 being our step 2. So in some of my problem sets, you might see this as a two-step process, but a lot of textbooks now just allow you to kind of write this as one step. Occasionally, you might see another reagent to help with it, NMO, but it's fine if we just write OSO4 if you're asked to fill in the reagents. All right? So looking at the reaction here, break the pi bond, add two OHs, make sure they're syn. In the top example, because we only have one stereocenter, I don't have to draw in my dashes or wedges. That is not a stereocenter. In the bottom example, we're going to break the pi bond and add the two OHs, and here we just have to note that they are syn, right? So they're both dashes or both wedges, right? Racemic means it can be both dashes or both wedges. So you could draw this molecule as such, where the two OHs are wedges, and that would be completely correct. And again, as we've talked about before, in my class, you only have to draw one of the enantiomers to do this, all right? What tells us on why this is syn, right? Again, this is the mechanism, okay? And for my class, I'm not going to actually ask you to draw the mechanism, okay? So I just want you to be aware of it. It turns out historically there's been some debate on what the mechanism is. So I'm going to show you sort of two options, with the second one being the mechanism that's more likely. Okay, so initially chemists thought that the mechanism involves sort of the cyclic rearrangement where the pi bond would break, form a new bond to O. The two electrons here would go onto the osmium, and then our double bond would break to reform the new bond. So this was originally one of the mechanisms that was thought to occur, where you add the O's at the same time, and then you're connected to both oxygens at once, and then essentially the O osmium bonds would break to get your final product. So historically, people thought that was the actual mechanism, right? New evidence now sort of suggests that that's not the case, where you have an O double bond to the osmium, and in fact the O adds and you form a species that kind of looks like a four-membered ring, something like this, to the osmium, here, and then one of these oxygens will then insert again on the same side, right, because we have this small four-membered ring, right? But in my class, I'm not really going to ask you these mechanisms. I just want you to understand this is kind of the two options on how this can take place. The second mechanism is more likely, but for us, you don't really have to worry about knowing these mechanisms. We just have to be aware of the reactions and this is a good way to get a syn, right? Osmium tetroxide gives us a syn-diol.